the recording, then yeah. So yeah, let's go over things that we are discussing last time. So we are discussing basically some of the ideas about the diffusion D models, so how we can implement the diffusion models to basically generate some images or some other kind of the data D modalities. And we also briefly discussed the pros and the cons of the different generated models. So what we could see was that GAN was kind of the most famous the generated models, which was basically able to basically generate the samples in a very fast, and also it was giving some kind of the very good quality of the samples. But it typically has some kind of issues in terms of like having some kind of the mode collapse issues, basically losing some of the diversity of the data, and also it was very unstable kind of the system in terms of that the training becomes like very unstable. And VAE was another kind of option, which was basically also kind of like giving some very fast speed in the sampling, and also does not have some kind of the mode collapse issues. But typically the quality of the sample was not that good. So that's why basically we also discussed the idea of the diffusion model, which is basically giving some kind of the high quality the outputs of the samples, also not having the issue of the mode collapse. But the problem of the diffusion model is that it is basically taking too much time, both for the training and the generation. So we have seen this example that while this was kind of the first diffusion model that basically beats the previous GAN model, the training took like too much time, and also even the generation of the data samples was also taking too much time. So to address this issue, we briefly discussed the idea of the latent diffusion models, which was basically nothing but basically doing some kind of the dimension reduction in terms like reducing the dimension of the input data by basically mapping all the things into the latent space using a autoencoder. And this was kind of some sort of the standard model that is basically being used in the many famous and the public diffusion models. So I guess most of you have heard about this diffusion model, which is the stable diffusion, which was basically trained with the very large scale data set. So I'm not sure how many of you have heard about this data set. This is basically the public data set, which contains 5.85 billions of the pairs of the text and the images. So you can see that the scale is really big. It's even not millions, it's billions, more than 5 billions of the text and the image the pairs. So basically we are now having this kind of some public data set, and also the pre-trained the diffusion models, which was trained with this kind of the very large scale image data sets. And that's why we could see some very high quality of the outputs of the generation. So you can actually try the stable diffusion yourself. So if you go to the Hugging Face, the kind of the webpage here, then you can also check out some more implementation, the details about the stable diffusion, and try to generate some kind of images yourself and see how much it works. So those are some kind of the very recent work in terms of like seeing the improvement in the generative models and some very high quality the outputs of these kind of the diffusion models. So the things that we were discussing last time is that how we can also reduce the computation time in the diffusion models, and especially how we can basically reduce the number of the iterations in the reversibility process. So that's kind of things that we were discussing last time. And for that, we also discussed the idea of the DDIM, which was basically making some kind of the changes in the DDPMD model in terms of that we are now using slightly different the forward and the reverse the diffusion processes. So in the DDIM model, instead of like modeling the forward transition, so in the DDPMD case, we are basically directly modeling this, like when we have the xt minus 1, like from the xt minus 1, basically we are getting the xt. So we are basically modeling this. But in the DDIM model, instead of directly modeling this, we are basically modeling this and this conditional probability distribution in a way that the forward transition can be defined as based on the base rule. And also we are basically making some of the these definitions with the new parameters, the sigma here. So it's not working on my iPad. Yeah. So we are also basically defining these two, especially the second, the conditional probability distribution, xt minus 1, given the xt and the x0, based on the new parameter. In terms of that, we can also even make some kind of the variations with this kind of for the processes. And other than that, actually, all the other processes are basically exactly the same. So we could define the reverse process in the same way by using this distribution. But the thing is that now we are changing this distribution, right? And also the way that, sorry, that we are training the model becomes the same. Exactly like we are having the noise prediction the model and using the same predicted noise for the generation, but we are only just changing the kind of the definitions of the reverse transition in a way that we can also still run the reverse process. So kind of some of the key important effects about the DDPM is that basically DDIM is basically kind of the generalized model of the DDPM with some kind of the additional parameters of the sigma here. So basically, if we set some specific sigma, then we can see that actually it becomes exactly same with the DDPM. So depending on which sigma that we choose, actually we can make the DDIM as kind of the same as the DDPM, as the same Markovian process. But basically, by varying the sigma of the value, we can also make the DDIM as kind of the non-Markovian process, so which is basically making some kind of the generalized version of the DDPM. And also, the most important thing is that while we are changing the forward and the reverse processes, the parameters of the reverse process, for the reverse transition, can be learned in the same way with the same training procedure. So which means that if we basically train the noise predictor, this network, taking the noisy input and the time step t, and then predicting the noise that was basically added to make the xt. So if we basically train this noise predictor using the same way as the DDPM, actually we can just directly use the same noise predictor, which was actually trained for the DDPM, for any DDIM generated process, for the arbitrary sigma. So that's the most important kind of effect. So the thing is that for the DDIM generated process, you don't need to basically train the different noise predictor. You can use the same noise predictor while basically running the different the reverse process, the generated process, even when you vary the sigma as you want. So that's the kind of the most important part. So that means that typical the diffusion models like the stable diffusion is basically trained for the DDPMD process, but for the pre-trained the stable diffusion model, you can actually run the DDIM, the reverse process, to basically run the different reverse process. And also the important thing is that you can actually make the DDIM process a kind of the deterministic. So if you basically make the sigma to be 0, then we don't have the part of like sampling the unique Gaussian noise, reverse the process, but everything becomes deterministic, which means that if you start from the specific x capital T, then there is no randomness in terms of that from the xt, everything all the process, the reverse the process is going into the more the deterministic way. So you just need to run the default process, the propagation of the noise, the predictor, and getting the noise, and all the computation becomes like basically deterministic. There's no sampling from the unique Gaussian distribution. So these are kind of the key facts of the DDIM. Actually, the goal of like introducing the DDIM is to make the deterministic degenerative process without basically doing some kind of the sampling in the unique Gaussian, while using exactly the same noise predictor model, which was trained for the DDPM. So here the question is that why we want to basically get the deterministic degenerative process. So that's kind of the actually the reason that why we are making the DDIM. And the reason for that is that actually we are talking about the speed of the generation. Actually, one of the ways that we can basically boost up the reverse process is that we are basically kind of like taking the samples of the time step. So let's think about that we are having the maximum the time step like 1,000. So in the forward process, we're gonna go over from the time step the t to the b1, from the 2 and the 3, and going into the 1,000, right? So this will be the forward process. And the reverse process, we are obviously going in the reverse way, starting from the t to be 1,000 and going down to 999 and 998, like all the things, right? So we're having the 1,000 steps. So one of the kind of the way that we can sort of like approximate this kind of the reverse process is basically sampling some of the time steps with some kind of the certainty intervals. So for example, like instead of like having all the 1,000 steps, we can consider like just we are taking the 50 steps by just taking some kind of uniform intervals, so like every 20 the time intervals. So we are talking from the 1000 and going down to 980, like 960. So in this way, we can basically reduce the number of the reverse steps while basically somehow approximating the overall kind of the reversibility process with the subsequence of the time steps. And also the thing is that even when you basically run the reverse process with the subsequence of the time steps, actually, getting the optimizing this for the given the data samples becomes like minimizing the same objective function with all the full sequence of the time steps. So it's basically not basically giving some kind of the bias for the final the outputs, but there will be become some kind of approximation for the full the reversibility process. So that's kind of thing. So indeed, this is kind of the XT-1 the computation in the DDIM the process. So the only thing that you need to do is that basically instead of like taking the XT and the alpha t here, like all these kind of numbers from the the previous kind of the time step, now we are getting some kind of the samples of the time steps and taking all these values from the some kind of the previous steps in the given the subsequence of the time steps. So that's kind of thing. But obviously, like this is kind of the approximation of the reverse process of the full the time steps. So as we basically decrease the number of the time steps in the subsequence, obviously the output, the sampling, the quality would get worse. And what people basically observed in kind of empirically is that as we basically make the reverse process more like the deterministic, actually the quality degradation for the basically reduce the amount of the time step is also minimized. So which means that when you basically decrease the number of the time steps from the 1000, for example, to the 50, actually basically make the reversibility process as kind of deterministic. There are not much kind of the randomness that we are adding over the process, right? Which means that if you take the xt, then x0 will be basically determined without any kind of the randomness. So for those kind of the cases, the approximation with the fewer number of the time steps becomes the more accurate. So which means that we are basically not sacrificing the quality of the outputs that much, while also dramatically reducing the number of the samples. So that's basically what people intended in the DDIM process. So if you see some quantitative results here, so what we can see is that each of the row here is basically some of the results that we are controlling the sigma value in terms of that. The first row means that this is the fully deterministic process. The sigma becomes the 0, the first case. And the fourth case here is basically exactly the same case with the DDPM. And even the last one is basically even adding some, using some bigger sigma than the DDPM. So adding some more stochastic over the reversibility process. So what actually we can see is that as we basically increase the stochastic in the reversibility process, at the kind of the beginning, when you use the full time step 1000, actually we can get some kind of the best results somehow. But the thing is that as we also reduce the number of the time steps, doing some kind of the approximation for the reversibility process, you can see that actually the quality gets worse. So here basically all the numbers are basically good when the numbers are basically small. So so these are the FID scores, which means that it's good as the numbers are basically smaller. So 3.17 is really small number, which means that the quality of the samples are really good. But as you basically decrease the number of the time steps in the subsequence, we are seeing that the quality gets really worse as we are adding some more the stochastic. But the thing is that if you basically make the process as the deterministic, then what we can see is that even when you use only the 10 steps out of the 1000, actually the quality degradation is not that big. So we are still kind of getting some okay results, but actually it's not very good. But you can see that if we basically reduce until like the 50, then there's no big difference, right? With the case that we are using the full time steps. Obviously, you can get the best results when you get the full time steps. So when you use the full time steps, this is like giving the best results. But still, when you basically only sample like 5% of the time steps, making all the reverse process like much faster, when you basically make the process deterministic, actually the quality is still kind of like becoming kind of preserved, even when you basically speed up all the process. So that was kind of the basic idea of the DDIM. So in the DDIM, the goal is that we are basically making some kind of the deterministic reverse process, which can be performed with the same noise predictor with the DDIM, while basically making the process to be deterministic in a way that when you basically accelerate all the sampling in the process with the reduced amount of the time steps, we can still get some kind of the good quality of the outputs. So that's kind of the basic idea, the DDIM. Any question on this? Yeah, so that was kind of the basic idea for the DDIM. So let me go over into one quick also idea in terms of like how we can also improve the quality of the data samples on the diffusion models. So these are also very famous the ideas, which is the classifier guidance and classifier free guidance. So the basic idea is that for most of the kind of the cases, especially for the images, we may basically have some kind of the extra information for all the images. For example, if you have any kind of experience with the ImageNet, ImageNet is also one of the kind of the large kind of the image data set, which is having some kind of the class information, right? For those images, basically, we have the information that these are all the dark images. So we are having the class label that these images are like the dark images, right? Then here the question is that, can you somehow utilize this kind of the extra information to improve the quality of the generation? So that's the basic idea for the classifier, the guidance. And for that, what we are going to see briefly is that basically in the diffusion model, what we are interested in is basically getting this kind of this core information, right? So previously, we are basically seeing this core information for the marginal distribution for the xt. But since now we are having some kind of the extra information, the y, let's say the y is basically the class label. So now we are going to get this core information for the joint the distribution for both the xt and the y. So when you know that the image that we want to generate is like this certain the label, if, for example, like when you know that we want to generate the dark images, basically giving some kind of the class label the information, how can you get this core information for the given the class label? So that's kind of thing. So if we basically decompose this core the function for the joint the probability of the noise image and the class label, then we can see that this can be decomposed into this form. So what we can see is that we are basically having this core for the marginal distribution for the xt. So that's basically the information that we could already get from our the noise predictor, right? And also we need some extra information about this, the second part. So let me clean up this. So this is the information from the noise predictor. And we want to basically get this information, right? So that we can get this core, the information for the joint the probability. So here the question is that how we can get this core for this like conditional the probability. And you can see that actually this is the conditional the probability about like the class label given the xt. So given the noise image at any intermediate step. So xt is any kind of the noise image at the intermediate step in the reverse process. So given the noise image, how likely that image will have the given the class label dy. So that's about basically this conditional the probability, right? So given the xt, how likely we're gonna get this specific class label? So that's basically the information that we need. So which is basically about classification, right? So here basically the information that we need to know is basically given the xt. So here, yeah. So given the xt from the noise image, what will be kind of the the likelihood for the given the class the label? That's basically the information that we can achieve using some classifier, some kind of the classification the neural network. So here basically what we are going to do is that we are basically getting this information by training another the classification the network that is taking the xt as the input and predicting the probability for each of the class label in a way that we can basically get this information. Then from this kind of the information that we learned from the classifier, the classification the network, we can basically get directly the information about this score by taking the gradient with respect to the xt, the noise, the image. So that's basically the way that we are basically approximating this information here. Just calculating this information using the classifier, and then using some kind of the updated this call function in our kind of the reverse process. So that's the basic idea for the classifier guidance. Here the question is that in the previous slide, the equation, how did the right term get the term square? So here the question is that why do we have this, right? So actually we have seen this. We have seen that these two are the same in the slides in the previous lecture. And this is nothing but we are basically taking this as kind of the one big term, which is multiplied by the coefficient here. So like these two, this and these two should be canceled out, so that we are basically multiplying this to the square function of the conditional probability. Does it make sense? Yeah, you can see that these are nothing but basically these and this core function. These two are the same. So we have seen this in the these two are the same. So I didn't see the big I can get the question here. Can you elaborate your question?
Sorry, I didn't see the big parentheses. Thank you.
Yeah. So yeah, basically, so these two are the same, and then we are rewriting this in a way that now this becomes some kind of the new epsilon dt that we're gonna use in our reverse process. So that's the basic idea. So in the reverse process, what we are going to do is that now we are going to use this as kind of the epsilon t instead of like the direct output from the noisy predictor. And then even we can try to somehow control the strength of the classifier, the guidance in terms of basically multiplying some kind of the weight here. If you basically make this W to be 0, then this becomes the same, exactly the same with the typical the DDPM or DDIM process. And if you basically make this W to be 1, then we are giving some kind of the classifier, the guidance, and even the W can be bigger than 1. So you can play with this, and this idea can be applied to both DDPM and the DDIM because they are all based on the noise prediction. Then you can see that the kind of the limitation here is that we need to train the additional classifier, the classification, the network, right? So it is taking a lot of the time, and also these should be basically trained after we train the DDPM, the model, right? Because we need to take all the XT as kind of the input. So this is not just kind of images, but the noisy image that we are seeing in the intermediate reverse process. And we need to take this as kind of input and basically train the classifier, which means that we need to train this additional classifier, the classification, the network, after we train the DDPM, the DDIM, the models, which is really taking the extra time to run all the things, right? So the kind of the engineering the idea that people basically have seen is basically is the classifier, the free guidance, which is nothing but it's really kind of some engineering the idea. Here the idea without any kind of some theoretic guarantee is basically here what we want to do is that we are jointly training both the conditional and also the unconditional different models. And the basic idea like making both the conditional and the unconditional models in the simultaneously is that we are just like making one unconditional models. So as we are taking the time step t as kind of the extra input in the noise prediction, we can somehow feed some kind of any kind of the conditional information. Let's say here is the class labels as kind of the extra input. So making some modification in the architecture of the noise predictor in a way that we are making some conditional diffusion models, taking the class label as kind of the extra condition. And for the unconditional case, we are just making a special the class label, which just indicates that this is kind of the case for the unconditional generation. So let's say like you have some kind of the index of the classes, like something from like 1, 2, 3, 4, like 1 is for the dog and 2 is for the bird, 3 is for the cat, or like 4 is for human, whatever. So you're gonna have this kind of the class, some kind of the indexes, right? And then we're just having like one more, some kind of the extra, the special the class label, which indicates that this is kind of the unconditional the case. So in this way, it's kind of like some sort of the engineering the way in terms of like jointly training both the conditional and the unconditional the different models. So then what we're gonna see is that depending on the extra the information that we are getting here, this will become the kind of the some specific the noise prediction for the given the label. And if we also control the kind of the the strength of the condition in some kind of the reverse the process, what we can do that is that we can do some kind of the linear combination for the noise, which is predicted for the given the specific the class label, for the noise, which is predicted for some kind of unconditional case, for the cases that we don't care about any kind of condition. So what you can see here is that as we basically, if you basically make this W to be 0, then this is the specific case that we are just taking this, the noise from the conditional the input as kind of the noise that we're going to use in the reverse the process. And if we basically increase the W to be greater, then even we are basically some kind of like giving some more the emphasis for this weight, no, sorry, this kind of this noise for the conditional case, while even basically being more deviated from the noise, which is predicted for the unconditional case. So this is like, there's no any kind of theoretical guarantee, but it's kind of like some more the empirical kind of things that in terms like by somehow combining the noise, which is predicted for the conditional case, and for the noise, which is predicted for the unconditional case. By making some kind of the linear combination of like these two cases, actually we can give some kind of strength for the conditional input. Empirically, this was giving some kind of the some better the results, which is really following the given the condition. So that is kind of the basic idea for the classifier free guidance. So as we increase the W, we are increasing the conditional the noise. As we increase the W, we are decreasing, even making this to be the minus for the unconditional the noise. So this is very engineering the idea. So what we can see is that so this is the DDPM case. Yeah, for the classifier the guidance when you train the additional the classifier. So this is also the number which is like the case that the smaller is better. So we are getting the 2.97, which is kind of the very good number, right? So as we basically control the W in the classifier of the free guidance, the 0 means that this is exactly the same with the unconditional case. And the 4 means that we are giving some really strong the emphasis for the conditional the noise, while even basically sacrificing the unconditional the noise. So as you can see that as we vary this W the weight, we are also seeing some all different results. And you can see that we can typically see some kind of the best results at this point. So in this case, when you give some kind of the strength for the conditional the noise, we are kind of even getting some better results for the classifier the guidance. While basically when you have some kind of the different weights here, sometimes even the quality get really worse. So those are also kind of the things. So depending on which W the weight we are choosing in the classifier free guidance, even we can achieve some better results than we are having the classifier the guidance. So this is really basically very practical the idea in terms of like how we can leverage some kind of the extra the class labeled information to get some kind of good quality in the generation. So the pros and the cons of the classifier free guidance is that actually it's kind of like very general the idea in terms of that you can actually feed any kind of the extra information. So it doesn't need to be class labels, but it can be any information which is basically associated with some kind of the data that you are generating. So for example, instead of the class labels, we can put the text description, whatever some kind of the extra information. So in terms of the classifier free guidance, it's basically more the general the framework than the classifier the guidance. And also the good thing is that you don't need to train the classifier the classification, the network after you train the DDPM or DDIM models. So that's kind of the good things. The downside is that in the reversibility process, basically you need to run the fault propagation of the noise predictor twice, because you need to get the noise of the conditional case and the noise of the unconditional case. So basically the reverse process will basically take some more time in terms of you are basically evaluating the neural network twice, right? And as you can see, also you need to choose the optimal weighted W. So depending on like which W you choose, actually the quality even get worse. So it's also very crucial to basically choose the optimal weighted W in terms of getting the best quality. So that's the basic idea in terms of how we can improve the quality and also improve the speed of the diffusion models. Yeah, this is really basic idea. Any questions on this? It's clear. No question. Then let me move on to the next slide. Okay, so far we have seen some kind of the basic ideas in terms like how we can basically implement the diffusion models, and also how we can basically boost up the quality of the samples and also the speed as well in terms of like using the ideas of the latent diffusion models, and also the DDIM, the idea, and also the classifier guidance and classifier free guidance. So those are all the ideas in terms of how we can improve the computation time in the diffusion models, and also how we can improve the quality of the samples at the end. So actually what we are going to discuss today is kind of main topic. I'm not sure whether we can cover everything. It's basically how we can utilize this kind of like pre-trained diffusion models for the many kind of the other applications, and also how we're gonna eventually apply this idea for the 3D generation. So that's kind of the main things that we are going to discuss today. So actually the good thing of the diffusion models, especially compared to the GAN and the VAE, is that actually it can be used in some many kind of the other some applications. So not only for some kind of the pure generation, but even for some kind of the conditional degenerative setup, like some kind of like these cases, like the making the images from some kind of the usual sketches, basically filling some kind of the missing regions from the given the images. For those kind of the some kind of the editing the applications, actually the interesting is that the pre-trained diffusion models, which is trained in a like unconditioned way, can be basically directly applied to this kind of some conditional cases, even without basically fine-tuning the neural network, or basically fine-tuning with some very few samples. So those are basically the zero shot and the few shot, some kind of the adaptation cases. So here the question is that even without basically fine-tuning some kind of the unconditional diffusion models, how are we going to basically apply those things for some kind of the conditional cases? And what if we can also basically fine-tune the models? What would be kind of the some effective way that we can quickly adapt the unconditional diffusion models for the conditional setup? So those are kind of the things that we're going to quickly see. For the GeoShot, the applications, like one kind of application might be is that how we can basically do some kind of the image editing using the different models. So those are some kind of the examples. Like we can allow the user to basically draw some kind of the strokes like this on the left-hand side. Yeah, so like this, we can basically allow the users to basically draw some kind of sketches for the strokes, and then we can basically convert those things into some kind of the realistic images. So you can see that the first row is the input, and the last row is the output, which is basically the realistic images that are basically close to the input, the strokes in the sketches. And also, even for some kind of given some realistic images, we can allow the user to draw some kind of these scribbles like this, or adding some kind of strokes in a way that we can also convert this kind of the composition of some sketches and the real images into the closest the real images. And for that, basically basically the things that we are going to discuss is basically all some very practical ideas without some kind of any theoretical kind of guarantees. But some basically very simple the technical kind of things that we can do would be basically just running some kind of the forward process and then running back the reverse process. So what we are going to do is that from some kind of the slightly unrealistic images, we are basically just perturbing this image, basically adding some noise through our forward process. But we are basically not adding the noise until the end. So if we have some kind of the time step from the 1 to the 1,000, then we can basically add the small noise until some kind of the amount of the time step until 50 or the 100 as you want. Then we are running back the reverse process for the amount of the time step that we tried to add the noise. So that's basically very simple and very practical the ideas. And actually what we can see is that if we go until the end of all the time steps, so if we start from the time d1 and if we go into the 1000, and this will be basically exactly the same the generation process, right? Then we are really going the full path of the forward process and going back of the full path of the reverse process. Then that will be exactly the same the reverse process. Then the thing is that we don't know what are the images that we're gonna get, right? While we basically started from some kind of specific image, if you run the process until the end and also go back to all the 1000 steps, then the output image that you're gonna get will be very different images, right? So that's the thing. But interesting is that if you basically run the reverse the full process for just like few amount of the steps, like 50 or the 100, then what you can see is that if you just run the reverse process back until the time stage 1, then you're gonna actually get some kind of results which is close to your input. So we are basically seeing some kind of results which is not deviating too much from the given the input image. But obviously, the kind of the drawback might be is that as you basically run the forward and the reverse the processes, like for the shorter amount of the time steps, the output may not look basically realistic. So basically, there will be some kind of the trade-off in terms like, depending on the amount of the time steps that we are running the forward and reverse the processes, you may get some kind of results which is really close to the input of some kind of that user provided, while the output may not look that realistic. So you may basically try to basically play with some kind of the amount of the time steps in terms of like what would be kind of the sweet spot in terms of that you are getting some kind of results which is close to the input that you are providing and also that also looks quite realistic. So that's kind of the very simple the idea in terms like we are playing with the diffusion model for some kind of the editing the setup. But this is really the simple the idea, and what we can go further is basically also trying this idea for the in-painting setup as well. So this might be slightly more complicated in terms like here the problem is that given the image, we are having some kind of the region that we want to fill in something, right? So given this kind of the input image, we have this mask, and we want to let the diffusion model to make the whole image, but just filling in this specific region while keeping the background. So how we can basically run the pre-trained diffusion model, which is not trained with such kind of the mask, but basically to run the reverse process in a way that we can just fill in the missing region while basically making some field information in this kind of the mask to be seamlessly connected with the background. So that's basically what we are going to do. So we're assuming that the foreground region is basically some of the missing region that we are going to fill in while basically keeping the background region. So for that, actually, there are some kind of the bunch of the ideas, but very practical kind of the idea here is that we are repeating interweaving the forward and the reverse the processes. So the thing is that we are going to combine some denoised the foreground the images, which is the region that will be filled in, and also combine the noise the images for the background the part at each iteration of the reverse the process. So what we can see is that we are basically we keep learning the reverse process for the foreground region that we are going to fill in. The thing is that for the background region, we are also running the forward process of the diffusion process and combining these two at each iteration. So let's go over with some each of the steps. So what we are going to do is that it's the same with the typical diversity process. We are starting from the xt. The xt is for the entire the image. And then at each time step t, we're going to have some kind of the, some noise image of the xt, right? And we basically run the, the reverse the process for the one step and getting the denoise the image of the xt minus one. So let me basically denote this as kind of the let me denote this as kind of the xt minus one of the foreground, right? At each time step. And while we are basically running the denoising for the foreground image for the one step, also for the background images, we are running the fold process until the time step the t minus one. So given the background image, we are also running the fold process, adding some kind of the noise, doing some kind of the perturbation until the time step the t minus one, which is basically giving us the xt minus one of the background. So we are basically having like noise image, which is coming from the background through the fold process, and also the noise image, which is coming from the foreground, which is actually coming from the reverse process until the time step of the t minus one. So we are getting basically the foreground, the noise image at the time step t minus one, and the background, the noise image is at the time step t minus one. And then what we do is that we combine these two by just simply taking some kind of some specific regions for the mask. So for the this image coming from the foreground, we are just taking the foreground the region by just multiplying the mask. And also for the other images, we are just taking the background region using the same the mask, the inverse the mask. So finally, we are getting some kind of the combined the xt minus one. Which will be used as some kind of the intermediate the noise images in the next step. So basically, we are repeating this process, right? So basically, what we can see here is that on the way that we are running all the reversity process, we are not just directly using each of the xt, the noise the images, but we are basically combining the noise images, which is also coming from the background, basically perturbed until the same amount of the time step. And then we are basically compositing these two images and using that as kind of the reversity process. So this is really the practical idea in terms of like how we're gonna fuse the foreground information and the background information and each of the time step t, or the t minus one, in a way that we are also denoising and also perturbing each of the foreground and background images with the same amount of the noise until the time step the t minus one, and doing some composition and then running that as kind of using that as kind of the next step, the noise images in the reversity process. So this was basically very simple, the practical ideas in terms like how we're gonna use the pre-trained the diffusion models for some kind of image editing, especially in painting. So yeah, so these are some of the results. So you can see that on the left-hand side, you can see some kind of the masks here. There's kind of a region that will be filled. And even for some kind of the extreme cases like this, we are just keeping some very small amount of the region while basically changing all the rest of the part. For those kind of the specific cases, we can see that we are really getting some kind of the seamless the outputs while really preserving the specific regions. So we are seeing lots of the variations in the for the foreground regions actually while basically keeping the background regions. And these are more some extreme cases here. So these are really cases that we are basically keeping every other the single line for each of the rows and the the horizontal the lines and also for the vertical the lines. For those kind of the extreme cases, actually we can see that we are basically recovering some kind of the input images. So which means that actually we can apply this kind of the idea for the super resolution as well. So if we basically assume that every other the pixel in the 2D grid is kind of the missing the pixel, we can run the in painting here, and in a way that we can basically run the image the super resolution, basically increasing the resolution of the images. Any questions on this? So these are kind of the very simple and the practical ideas. But here basically, so what we can see is that these are all the cases that we are using some kind of the pixel representations of the images. While actually we could see in the LDM, in the latent diffusion model, is that actually latent diffusion model is really effective to basically get some high quality the outputs. Right? So there are basically the pros and the cons in terms of whether we use the latent representation or the some pixel representation for the image generation. So if we use the latent representation, the thing is that obviously we can get some better quality of the output, the images, because we can do some kind of the dimension reduction. But the thing is that we cannot directly apply the idea of the SDEdit and also the repaint in terms of like doing some kind of the manipulation in the intermediate step of the reversibility process. Because we are just playing with the latent, the feature vectors for the data. So if we want to basically make some kind of the conditional degeneration the process, actually we need to train another diffusion models for that. So which is basically not good in terms of that we cannot recycle the unconditional diffusion models for some other applications. The kind of the cons of the pixel representation is that obviously we cannot get some kind of the best quality of the generation of the outputs because we are playing with some very high dimensional some input data. And also the downside is that we cannot also change the resolution of the data. So if we basically have some kind of the latent representation, we can somehow make it as kind of some implicit representation that we are discussing in the previous lectures. In terms of that, we can also change the resolution of the data as we want. So that's kind of the downside. But the good thing is that if we have some diffusion models trained with some kind of some explicit pixel representation, is that we can directly utilize some unconditional diffusion model, some kind of the conditional setup without any kind of fine tuning. So that's also kind of some interesting idea here. Some pros and the cons in terms like which representation we're going to use for training the diffusion models. Is this clear? And also one kind of this quick idea, which is also about the guided, the reverse the process, is that, so this is also something that we can try in the reverse the process. So this is like typical degeneration the process, both in the DDPM and the DDIM, the reverse the process, right? So starting from the XDT, capital T, we are going from the reverse way, from the time step, in a way that we first predict the noise, epsilon dt here. And based on that, we are basically getting some kind of the prediction of the final output, the x0. And then we are sampling some kind of the noise from the unit the Gaussian. And based on like this information, the current, the noise image, and the prediction of the final the output, and also the noise sample from the unit Gaussian, based on these three information, we are basically computing the xt minus 1. So that's basically the common, the reverse the process, in both for the DDPM and the DDIM. For the DDIM, if we make this as kind of deterministic step, then we don't need this G, right? Adding this is basically adding the stochastic. So basically, both for the DDPM and the DDIM, basically we are basically computing the xt minus 1 based on the current, the noise image, or the noise data that we are having, and also the prediction of the final the output, which is computed from the noise prediction, and also the sample from the unit Gaussian, right? So here, what we can actually see is that the interesting kind of thing here is that given any kind of the noise the data that we are having in the intermediate step, actually before we go over the entire reverse process, we are actually getting some kind of the prediction for the final the outputs. So can you see this? So that's kind of the things. So even before we run all the entire reverse process, for each of the xt, for the noise the data in the intermediate step, we are getting some kind of the prediction for the final the outputs. But obviously, this final output may not be the same thing with the output that we're getting at the end. But it's kind of like getting some kind of the prediction for the noise data that we're having in the intermediate step. So that's kind of the key thing that we are doing in the reverse process. So here the basic question is that since we are getting some kind of the prediction for the final the output at each intermediate step, can we add some kind of the regularization about for the final the outputs in terms of what's the kind of the output that we want to see? So let me actually visualize this kind of the data points here. So this is kind of like one of the examples that we are having some kind of the noise image at the some arbitrary time step t. So actually these are some of the images that actually we could get in the real reverse process, and these are some of the results at the very beginning step. So from the 1000 to the going down to the 1. Actually, these are some of the images at the not this one. So actually, these are the DDIM case that we are reducing the number of the time steps to the 50 to the 1, just like taking the 50 samples out of the 1000. And this is the case that was like getting some of the images from the time step 45 in the DDIM case. So these are the images in the beginning step. So you can see that these are some of the outputs of the noise images. And then actually using some kind of the noise prediction, we can get some kind of the prediction of the final output. And you can see that these are some kind of the blurry output that looks not that much realistic because of some kind of some blurriness here. But if you actually see that what will be the final output at the end of the entire reverse process, is that these are some the final outputs. You can see that actually even the prediction of the final output at the beginning step is kind of close to the final output that we are going to get over the entire reverse process. While obviously this prediction cannot be that accurate. So these two are not exactly the same, but you can see that these are kind of close to each other. So in the cases of like adding some kind of the guidance in the reverse process, then what we can do is that we can add some kind of some regularization, which is basically meaning that given some kind of the prediction of the final output, we can define some kind of the objective function. For example, we can apply this idea of the in-painting as well. We can basically somehow enforce that the final output has the same colors in the background region. So minimizing the L2 loss for the background region. So that can be kind of the guidance. So it's basically a matter of like how we define the objective function here. Makes sense? Or we can basically match the style of the output images by somehow minimizing some kind of the style loss with the output image that we are generating with some kind of some reference image. So it's really matter of like what sort of the objective function that we are having here. So by just taking the prediction of the final outputs, we are running the backpropagation with some kind of the objective function that we defined in a way that we are basically updating the xt with some kind of the prediction of the final outputs. And then we recompute all the things and then just running the reverse process. So here the basic idea is that over the entire reverse process, when you have some kind of the noise data at each of the time step, we are basically adding some kind of the guidance based on the prediction of the x0, some kind of the prediction of the final output in a way that we are basically just pushing each of the noise data, the xt, to be basically making some trajectory with some kind of the outputs that we want to see. So that's the basic idea for the guided the reverse process. So there are some kind of lots of the work using this idea, and so one of the things is actually our research. So this can be also used in some kind of the panoramic image degeneration in terms of basically So these are some of the examples that we are generating some kind of the multiple images with some kind of the overlap in this kind of the big the canvas. While basically we are minimizing this kind of the seam across the frames and also minimizing the style difference with some kind of the guidance in the reverse process. And also the same idea can be used in the video editing as well. So let me replay this. On the right-hand side, these are also some of the results of like editing the given the video into some specific style. And we can also run the reverse process for each of the frame or the videos in a way that their style can match, basically adding some kind of the guidance in the reverse process. And the same idea can be also used some kind of all the other conditional cases for the in-painting versus for resolution for all the other cases. Basically, we are adding some kind of the guidance in terms of that. We are basically want to see some kind of the final output that basically satisfies some kind of a certain condition. And the condition is now given as kind of some loss function, the objective function here in this process. So that's the basic idea for the reverse the process. Any question on this? Yeah, so I just wanted to quickly go over some kind of the basic idea in terms of like how we can apply the unconditional diffusion models for some kind of the conditional cases. And these are some of the examples that we can immediately directly apply the conditional models for some unconditional models for some conditional cases. And also there are some kind of the other cases in terms like how we can even do some kind of the few shot adaptation. So how we can fine tune given the unconditional diffusion models in a way that we can even improve the quality of the outputs for some conditional cases. So also let's think about some kind of some conditional cases without the few shot examples. So this is like one of the kind of example in terms like doing some image generation based on the image condition. So these are some applications like some colorization, in-painting, uncropping, some JPEG rasterization. For those kind of cases, given some kind of the input on the left-hand side, we are basically generating some kind of the outputs, basically that are aligned with given the input images for each of some applications. So these are also kind of same, like in the noise predictor, we are taking the xt and the time t, right? So also we have seen the example of the classifier, the free guidance, which is basically adding some kind of the extra input here, like the class label. And then we can consider basically adding some kind of the extra input as the image condition, adding some kind of the condition of the image, and basically feeding them as kind of the extra input. I mean, there might be some kind of some lots of the choices that we can make for the architecture for such kind of the cases. So what they propose in this specific the work is that they are basically proposing to basically concatenate given the conditional image with the noise image that we are basically running the feeding to the noise predictor, just making some kind of the multi-channel kind of images by combining these two and just running the same UNet. So this is kind of like one specific, very straightforward extension for making the image, the different models conditioned by the another images. Obviously, the downside for such kind of the cases is that we need to basically have lots of the input and the output the pairs, right? If we want to basically train this kind of the neural network, we might want to basically have some lots of the input and the output the pairs. And we also need to train the different models from scratch. As I said, there are many kind of some public different models which are basically trained with the more than 5 billions of kind of the images. While basically if we consider some specific scenario of some conditional cases, the amount of the data would be obviously way smaller, like having some kind of thousands or tens of thousands of the images would be really way smaller than 5 billion images that were basically used to basically train the stable diffusion. So here the question is that how can we leverage some kind of the unconditional some different models, which is trained with some much larger scale data set, while basically adapting that into some kind of the conditional cases. So I'm not sure how many of you heard about the ControlNet. Even some people working in some kind of the design kind of the industry are now, as far as I know, they also now very familiar with this kind of the idea of the ControlNet, because it is really used in some kind of the design process these days. It's really practical tools. I guess most of you might hear about this kind of the idea. But basic idea of the ControlNet is that we want to basically just like adapt some kind of the pre-trained unconditionally diffusion models, especially the image diffusion models, like the stable diffusion, in a way that it can basically take some kind of the image condition. But in case like when the data that we are having, the input and the output the pairs, the number of these data is much smaller than the data set that has been used to train the unconditional cases. So when you only have like very small amount of the input and the output pairs, like less than 50,000, how can we leverage the stable diffusion, which is trained with the 5 billions of the images in a way that we can get some kind of the good quality of the images. So these are all the examples that we are taking the sketch as the input and generate some kind of the some variations. Or we are taking the human pose information as kind of input and generate some kind of the variations like this. So here the key idea is that we are basically fully somehow leveraging some kind of information which is encoded in the pre-trained the noise the prediction the unit the architecture in a way that we can process the conditional the image. So if we briefly go over into some of the details in the architecture, we can see that basically like for the encoding. So let me see. So this is the conditional the input image, right? And here, this input, can you guess what's the input here? So the left-hand side is basically the noise prediction in the network, right? Then what should be input in the noise prediction in the network? Question? So the left-hand side here is the noise prediction in the network, right? Then what's the input of this in terms of the mass notation? I mean, when this is the noise prediction in the network, what should be this input? So what I'm saying is that basically this is the noise prediction T network, right? Epsilon T. Then obviously input here will be basically xt, the noise image at each of the time step. And also we are feeding the time information here, T, right? Through the time encoder, which is like fed into each of the residual block in the unit. Makes sense? I mean, this was basically the architecture that we have seen in the previous lecture. So we are having the noise predictor, which is taking the xt, the noise, the data as the input with some kind of the time t here. And also as kind of the extra the condition, we are also getting the prompt as well, some kind of the text description of the images. So as I said in the classifier, the free guidance, instead of the class label, we can also take the prompt as kind of the additional the information. So this is the architecture that we are taking the xt and also the time t, and also the the text description, the y as well. So xt time t and the y as well. And then predicting the epsilon t, the noise. And based on that, we can predict the x0, and then we can basically sample the xt minus 1 based on this information, right? Clear? So that's what we are doing. So from this kind of the architecture, as you can see, so this is kind of the unit architecture, which is taking the noise image, the xt. So we are having some kind of the some image encoder, which is now encoding xt information. So here the basic idea is that we want to somehow fully exploit all the kind of the parameters that are basically learned for this kind of unit architecture in order to basically process the conditional the image here. So the conditional image here is basically C. So what we do at the first this stage here is that we basically copy all the parameters of this architecture to basically make some kind of the encoding the network, which is now encoding the conditional image C here. So here all the idea is that we want to like somehow exploit the some learned the parameters of the given the unit to basically process the conditional the images. So we basically copy all the parameters like this part to basically make the encoder of the conditional the image, while basically we also allow all the parameters to be updated over the fine-tuning step. But we are starting from the basically the parameters that are basically exactly the same of the encoding the network. And the second part is the most important part. So in the second part, we are basically now combining the encoded information, the conditional images, into the original DUNet, the prediction of the network, through the layer, which is called the zero convolution. So which we're gonna, the things that we're gonna get into some details. So now what you can see is that for each of the residual block, so if you see like for these specific blocks, and somehow you can see that all the kind of the blocks are kind of same, that we are having this specific block. And for basically updating each of the block here, then we are taking the condition here, passing that into the zero convolution, and also basically processing that with the same kind of the processing the network, and then applying the zero convolution again, and feeding the output into the residual block here. So we are repeating this process. Then we need to see like what's the meaning of the zero convolution. So zero convolution is basically nothing but basically some kind of the affine transformation with the single the scalar number of the scaling factor, and also the bias, the offset. So you can see that basically in the kind of the formulation, x might be some kind of the vector representing each of the input to the layer, and we are basically scaling, uniformly scaling the input vector with the scalar value, and also having the one single value for the offset. So making some kind of affine function. So in terms of like implementation, this might be the case that we are having the one by one convolution layer, which is basically applying the scaling factor the A into all the numbers in the input vector, and then adding some offset, the bias B here. So nothing, basically having just like two numbers, A and the B, and scaling the input vector and adding the offset. So the reason why we call this a kind of zero convolution is that we are initializing both of the A and the B to be zero, which means that whatever input you feed at the very beginning, before you start the fine tuning, the output will be zero. So we are starting from some zero initialization for the A and the B. And then what we do is that based on this, we are making this kind of the architecture here. This look a little bit like complicated, but let's go over into some of the details here. So at the very beginning, what we do is that at the beginning, from given the condition of the input, we are feeding this into the zero convolution. Then at the beginning step, before the fine tuning, what we're gonna get is that we're gonna just get the zero, right? Because those in the parameters for the zero convolution, the layer, these are basically the initialized with the zero, right? So the input, basically, the output of like this zero convolution will be basically zero, right? And then we are basically adding the output of this zero convolution to the X, and then feeding this into some kind of the network, which is basically the copy of the pre-trained network, right? So we are adding the output of the zero convolution to the X. Then now this should be exactly the same with the X, right? At the very beginning, before the fine tuning, because the output of the zero convolution will be zero, right? So taking the same output with the original the noise prediction network, and feeding this into the network, which is the copy of the existing network, which means that the output of like this part will be also exactly the same with the output of the original network at the very beginning, before the fine tuning, because of the parameters are basically copied from the existing network, right? Is this clear? So we went until down to this part. And we are also feeding this output again into the zero convolution here. Then now also the output will be like the zero, because also these two parameters for the second zero convolution is also initialized with zero, right? And then we are feeding this back, basically just like adding this to the output of the original neural network. So this is the original residual blocks of the noise prediction network, and adding this to this one. And since at the very beginning in the fine tuning step, since this will become zero, the output of this, like the whole block, will be exactly the same with the original D architecture, right? So that's kind of thing. So this is kind of the very practical the idea in terms like how we start for some kind of the good results before we run any kind of the fine tuning. So here the basic thing is that we want to start the fine tuning the process in a way that before do any kind of fine tuning, before running any kind of fine tuning, the initial state of the neural network becomes exactly the same with the unconditional decays. So we are starting from there, basically making some kind of the realistic data without taking any condition. So that's the thing. So what we want to do is that we want to fine tune our the network in a way that we can gradually basically adapt some the conditional the inputs while still making some kind of the realistic data. So we are not breaking the neural net in terms of like making some kind of big changes. So we are starting from that. We are still making some all the realistic outputs while not taking any the conditional information. But over the fine tuning, we are gradually updating the parameters in a way that we can basically adapt some kind of the conditional the input information while still maintaining the neural net to basically produce some realistic data. So that's kind of sort of the philosophy in terms of the neural net the architecture design, some kind of the practical way. So we want to basically make the neural net to be basically produce some realistic the output images all the time over the fine tuning by starting from some kind of the initialization that is already basically becomes the same with the unconditional decays. And also the thing is that as you can see in the second block here, in terms of like processing the conditional the input for this like the processing the steps, we want to also basically fully utilize the kind of the given the pre-trained unit in terms of the like we are processing beginning from the state that the network becomes just like the same with the unconditional case. So not taking the conditional the input, but just taking the original the input the xt. But while basically we are gradually basically adapting the neural network to be able to basically somehow basically feed some kind of the conditional the information because here in the zero convolution the layer, yeah. So in this case, while we are basically starting from the zero here, well, this is zero and this is the zero, over the fine tuning, these numbers will be adapted in a way that we are basically the output of the zero convolution becomes not zero, but some kind of the input that we are getting from the conditional the information. And then we are gradually basically adapting all the architecture in a way that we can also process the conditional the information while basically combining that with the original the input using some kind of the same architecture so that the architecture can be also easily adapted from the original condition, from the original the unconditional the case. So basically, this is kind of the architecture choice in terms like how we can make some kind of the incremental changes from the unconditional the case to the conditional case without breaking all the network architectures. So you can see some kind of the evolution study here. So the A is the ControlNet case. So if you do not use the geo-convolution layer here, then you can see that the output is becoming some kind of the unrealistic kind of results. And also, if you do not basically copy the neural net parameters and just directly feed the condition of the information without some kind of some processing the part of the condition of the images, you also still cannot get some kind of the realistic images. But when you basically carefully choose all these kind of the some design the parameters in a way that the network can be really gradually transformed from the unconditional case to the conditional cases, then you can basically easily adapt the given the network in a way that can now process some kind of some conditional images. So that's kind of some practical idea in terms of like how we can make some kind of the fusion adaptation of some unconditional models. So I guess, yeah, so I still have some few more slides that, to cover some kind of some editing setups. And actually, even we also didn't go into some 3D generation cases. So I think I need to stop here, and we're gonna go over with some kind of the remaining slide in the next Monday. And also, if you have any kind of something that you want to discuss about your project, please join the office hour the next Monday, and let's chat about your projects. Any questions on this? Any questions for any materials that we discussed today, or some plans for the next week. Is everything clear? So if you have any questions, please post the questions on the questions channel on this slide so that we can also discuss there. Then I will see you next Monday. Okay. Bye.